Hello, welcome back to another episode of Math with Haas. You are watching Precalculus Season 2, Episode 13, Part 2. We're continuing investigating the graphs of the trig functions. So, in the previous video, in Part 1, we looked at the graph for sine and cosine. In this video, we are going to look at tangent and cotangent. So, let's start by, we'll put a brief unit circle up here, and by brief I mean about that brief. So there's 0 and pi over 2, and I'm actually going to call this negative pi over 2. It's the same thing as 3 pi over 2, sort of, as long as we keep in mind that this is negative pi over 2. So there's our negative pi over 2. We have to go counterclockwise. Clockwise, counterclockwise, this is 3 pi over 2. So it's the same thing in terms of xy coordinates, but how we get there is different. Alright, so tangent, y equals tangent theta. So we can start by making a table of values, right? So we can note that when theta is 0, for example, well, tangent, if we recall, tangent theta is equal to sine theta over cosine theta. So tangent of 0 is equal to sine of 0 over cosine of 0, and sine of 0 is 0, so that means this has to be 0. And when we think about pi over 4, tangent of pi over 4 is sine of pi over 4 over cosine pi over 4, and for both sine and cosine that is going to be square root 2 over 2. So square root 2 over 2 divided by square root 2 over 2 is going to give you a 1. And we can work that out. Tangent of pi over 4 is equal to sine of pi over 4 over cosine pi over 4, which is equal to root 2 over 2 over root 2 over 2, which is equal to 1. So that's our justification for that. And there's going to be a reason why I'm interested in negative pi over 2, but for the moment we'll just continue this way with pi over 2. That's a terrible looking pi. Alright, let's see if we can fix that. And nope, can't fix that. Alright, so when we consider pi over 2, this is where it's very important now to consider this ratio. So tangent pi over 2 is equal to sine of pi over 2 over cosine pi over 2. Great, except that, well, we call that sine of pi over 2 is 1, but cosine pi over 2 is 0. Red flag. You cannot divide by 0. So first we're going to put u and d here for undefined. The second thing we need to note is this tells us there is a vertical asymptote. Vertical asymptote. Asymptote. Alright. So now that causes a problem. So let's back up a moment. We saw that when cosine was 0, it causes a problem because we cannot divide by 0. So we need to figure out, when does this denominator equal 0? Well, another situation is if we go either 3 pi over 2, because this x coordinate is 0, or negative pi over 2. So negative pi over 2 is going to cause us another problem where it's undefined, and we get this vertical asymptote. So let's box this. Vertical asymptotes at these coordinates, or I should say at these angles, and all their coterminal angles. Alright, we'll come back to this in a moment. So let's go ahead and start graphing. And I think I want to get a value in between 0 and negative pi over 2. So let's pick negative pi over 4. Well, negative pi over 4 is going to be right here. And that's going to be the same thing as tangent of 7 pi over 4. And I claim that's going to be a negative 1. And reason being is sine and cosine are both going to be root 2 over 2, except sine is negative in quadrant 4. That's where the negative comes from. Alright, with that, we are ready to start making a graph. So, let's see here. So, we can note that at pi over 4, we have a value of 1. At 0, we are at 0. And at negative pi over 4, we are at negative 1 down here. Cool. Now, we know that at pi over 2, which is hanging out here, and negative pi over 2, we're going to use red to denote do not pass go, do not collect $200, do not graph past the asymptote. So with the asymptotes, that means our graph cannot cross this red line. So literally do not cross the line. Alright. So we got to figure out what is going to happen in between pi over 4 and pi over 2, but not including pi over 2, because we have that asymptote, because we cannot divide by 0. And similar over here, we got to figure out what's going on. For now, we can just note, we got something like this. That looks terrible. I'll do that. Let's see here. I like that better. Still looks bad, but we will use Desmos to make it look better. Alright. So there's our preliminary graph so far based off our table of values and our asymptotes. Now, what we need to do is consider the following. So, let's think of our question this way. Let's get a new color. Alright, so we'll use this awesome pink. So let's think about what's happening as we get closer and closer to this point right here. Okay, this nice big pink point. So as we are getting closer and closer to here, as our angle gets closer to pi over 2, so I'm going to use this arrow to denote that as theta approaches pi over 2, well, sine of theta is going to get closer and closer to 1. So as theta gets closer to pi over 2, then sine of theta is going to get closer to 1, right? Because the y coordinate here is 1. In fact, let's get that up here. 0, 1 is our coordinate. And we know that cosine theta is getting closer and closer to 0. So we need to let this fact right here sink in. In fact, it's important. We'll make it rainbow. Important. Not really rainbowy. There we go. There's our rainbow. Alright. We've completed our rainbow. Awesome. I like it. Alright. So, okay, that's annoying me now. Let's delete that. That was looking awkward. Alright, so we'll use orange. Yeah, alright. So, when we think about this, because cosine's getting closer to 0, that means we want to imagine these decimal values, right? So at one moment we have a 0.1 for our cosine output, right? That's going to be somewhere right here. But then we have x values getting closer and closer to 0, right? So 0.01 is going to be some x value for some angle. And we can get ever smaller values, right? Because we're getting closer and closer to 0. So we can get ever smaller values like 10 to the negative 200 or something, right? It's astronomically small. And then that's going to cause a problem. In fact, we now need to think about, well, hold on. What is going to happen when we consider the ratio now? Because we have sine theta over cosine theta. And this is going to behave like a 1 divided by 0. But remember, the denominator has all of these itty bitty values, right? Because as this is getting closer to 1 divided by 0, that denominator is getting really, really small. So what happens when you have, say, 1 divided by 0.1? Well, that's 10. Well, 1 divided by even smaller number, 0.01? Well, that's 100. And 1 divided by 0.001, that's 1,000. Uh-oh. These values are getting huge. So these ratios are going to get bigger and bigger and bigger. When we consider our denominator, as it gets smaller and smaller and smaller, our values get bigger and bigger and bigger, which means that as our angles get closer to pi over 2, our y coordinate or our tangent outputs just shoot up towards infinity. They will get closer and closer, this line, to pi over 2, but it will never touch, it will never cross, because pi over 2 here is an asymptote. And we're going to get a similar situation over here. Now, oops, we can undo that move. Now, pi over 2, we are in quadrant 1 here, so that's important to note. So this is quadrant 1. That's important because in the previous video we talked about how, well, I should say 2 previous videos ago, we talked about how tangent is positive in quadrant 1, but tangent is negative in quadrant 4. So as we get closer and closer to negative pi over 2, so we're going this way now, that means our ratio here that's getting infinitely larger is now negative, because sine is negative down here, and a negative number divided by a positive number is still negative. That means instead of a 10, it would be like a negative 10, because that's negative, 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 all the negativity there. So that means this thing here is going down like this. And again, our sorry, allergies. Alright, so again, we're going down to negative infinity. We are not crossing the asymptote here. Our vertical asymptote we can never touch or cross. We can just get infinitely closer to it. That's our negative pi over 2. Now, with that, we can now enjoy the Desmos graph, because that is atrocious. And voila. So, just like last time, we talked about how there's a period, right? So if we imagine this is our graph, right? This is what that is replacing. It looks so much nicer. And if we zoom out, we can see the same things happening over and over and over. And the reason for this is because we can keep going around the unit circle, right? In fact, from here to here, that's all going around half of the circle, right? If we get our picture over here, right? We've only gone around the right half. We haven't even gone around the left half. So what that means is the period is actually going to equal pi. Or if you imagine distance from this asymptote to this asymptote, that's half a pi plus half a pi, or just pi. So for our y equals tangent theta, we can note that the period is going to equal pi, and we can note, well, see that we gotta figure out domain here in a moment, but we can see that the range is going to be negative infinity to positive infinity, because we can get every single y value just within this little subsection here. Now, back to the Desmos graph, we got this particular problem. If we zoom out, we can see, oh my gosh, there's an infinite number of asymptotes for tangent. That's pretty sweet. It's not every day you find a function with an infinite number of asymptotes, and yet we have found one. So that's pretty cool. So if we think about this asymptote, we know that we can't include this pi over 2, right? Now the distance from this pi over 2 to this asymptote here, that we said was pi. So if I add 1 pi, or in this case subtract 1 pi to get this one, that gives me this asymptote. And if I want to go the other way, next asymptote is going to be over here at 3 pi over 2. And then if I want to get the asymptote past that, that's going to be another pi. So in order to find all the asymptotes, we need to keep adding multiples of pi. So how we write this is, we're going to erase that pi. So we're going to have to multiply it by integer multiples of pi. Alright. So this right here, if we understand that n is restricted to be an integer, well, if I take pi over 2 and add 1 times pi, that's going to give me this one. If I take pi over 2 and add 2 times pi, that's going to give me this one over here. And since we're including integers, that means we can have negative values, right? So pi over 2 plus 1 negative pi, well, that's going this way to right here. And so this will give you all the asymptotes where they're at. So our domain is going to be all real numbers except our asymptotes, which are at pi over 2 plus n pi, where n is a integer. So what this is saying is where n is an element of the integers, n element of integers. Remember, we had this r here for real numbers, we have this awesome z here for integers. Alright, so tangent is a little bit more complicated than sine and cosine. The reason for that is because of this ratio here. Alright, it's time to look at cotangent. So cotangent is going to be very similar. So instead of thinking about when cosine was 0, we want to think about when sine is 0, because cotangent is cosine over sine. So when we think about when sine is 0, that's going to be at 0 and pi, or from pi to 2 pi, but we're going to look at from 0 to pi. So looking at this, we know at 0 we're going to have our asymptote because we cannot divide by 0, and we know over here at pi. So there's our pi, there's our other asymptote, and let's extend this line now. Now, when we think about pi over 2, that's when cosine is 0. So that means right here in the middle, that's pi over 2, and there's our first point. That's when our graph is 0. Alright. So when we think about quadrant 1, that is the values right here, right? From 0 to pi. Well, those are positive. And when we recall the argument we made, the closer, well, similar to tangent. So we want to think, closer we get to 0 or our angle of 0 radian, it's going to be a similar situation where we have this ratio 1 divided by a ever getting smaller denominator, something like that. which means we're going to get closer and closer to infinity. So this is going to shoot up like so towards positive infinity. And then when we consider going over here, cosine in quadrant 2 is negative. And so as we get closer to pi, we're going to shoot down towards negative infinity. So there's our graph. It's very similar with tangent. Alright, so there's cotangent. And we can denote our domain and range. So cotangent theta, domain. It's going to be very similar. And if I start here at 0, then note it's going to be all real numbers except in pi, where n again is an integer, where n is a integer or an element of the integer. So when n is 0, that's here. When n is 1, there's pi. When n is 2, that's 2 pi, 3 pi, 4 pi, etc. Our range again is going to be negative infinity to infinity. I don't know why I just wrote negative infinity to infinity. I could have also just wrote all real numbers, so that's a terrible looking R. So there's all real numbers. Either way, you can express it. And then we need to figure out our period. So we want to look at the distance for in between our two asymptotes. That's going to be a distance of pi because we are at 0 and we're stopping at pi. So that tells us our period is pi. Period is equal to pi, and we can note that our graph is going to repeat again and again because you just keep going around our unit circle. So let's go ahead and turn all this off, and there is our cotangent. Lovely. Yeah, so there's cotangent, and we can see there's a similar relationship going on between tangent and cotangent. Looks like a reflection and a horizontal shift. That again will require further investigation to verify, but at the very least it seems quite plausible. Alright, and with that, we're going to conclude this video. So if you've been enjoying our content, please subscribe, consider supporting us on Patreon. Thank you for joining our math party, and I will see you next time.